Statistical Institute, who will talk about isometric dilations, models, and refined von Neumann inequality for a class of tuples in the polydisc. Welcome, Sibaprasad.
Thank you, Ilavinda, for the introduction, and also thank you, organizers, for giving me the opportunity to speak here. So I will be talking on isometric dilations, models, and refined von Neumann inequality for a class of tuples in the politics. And this is a joint work with Professor V.K. Das, Professor Joydesh Sarkar, and Kalpesh Haria. Let me tell you why dilation is important in multivariable operator theory. Basically, in many situations, dilation enables us to reduce problems of tuples of commuting non-normal operators to simpler problems involving tuples of commuting normal operators, in particular unitaries. One such problem is when an n-tuple of commuting contraction satisfies the von Neumann inequality. So what is von Neumann inequality? We say an n-tuple of commuting contraction T satisfies von Neumann inequality if operator norm of Pt is dominated by the subnorm of the polynomial P over the unit polydisc, and this happens for all polynomial in n variables. So question is when an n-tuple of commuting contraction satisfies von Neumann inequality, and this question can be answered partially through isometric dilation. It has been seen that if a tuple of commuting contractions has an isometric dilation or a unitary dilation, then it satisfies the von Neumann inequality. So what is dilation? Let's say H be a Hilbert space and T acting on the Hilbert space H be a contraction. That means norm of T less or equals to 1. An operator V acting on another Hilbert space K, where K contains the Hilbert space H, is called a dilation of T if T power K is the compression of V power K for all non-negative integer K. And compression means it is the composition of projection and the operator and the restriction. So whenever we have this kind of relation, Vk has the following matrix form. Vk can be written as this component, it is Tk, and here it is something we don't care about, and this holds for all non-negative integer K. So what does this expression tells us? This representation tells us that we can have T as a part of V. Not only that, we can have T power K as a part of V power K for all non-negative integer K. And whenever we have this kind of representation, we say V is a dilation of T. And sometimes we call this dilation as a power dilation. When V is an isometry, then we say V is an isometric dilation of T. And when V is a unitary, then we say V is a unitary dilation of T. What are the examples of dilations? So extensions are dilation. Let's say V be an extension of T, then one can check V has this matrix form. This component it is T, and here it is 0, and here is something. Now taking power in both sides, we have V power K equals T power K, and still this component will be 0, and here is something. So and this happens for all non-negative integer K, and this representation immediately tells us that V is a dilation of T. Similarly, coextensions are also dilations, and sometimes we call coextensions as lifting. So what is coextension? V is said to be a coextension of T if V star is an extension of T star. Then V star has this matrix form. Here it is T star and here it is 0. And then taking adjoint in both sides, we have V is T0 star star. And then taking powers, we have V power K equals T power K. Here it is 0 and here is something. And this representation tells us that V is also a dilation. So extension and coextensions are dilations. Now here is the definition of dilation in multivariable setup. For that, first we define T and H. For a Hilbert space H, T and H is the set of all n-tuple of commuting contractions. That means it is the set of all n-tuple T1, T2, Tn, where each Ti's are contraction and they commute with each other. And for an n-tuple of commuting contraction T, which is T1, T2, Tn, and for an multi-index K lies in the semigroup of all non-negative integers, semigroup of all n-tuples of non-negative integers. T power K is defined in this way. T power K is the composition of T1 power K1 up to Tn power Kn. And with this definition, we define the dilation in multivariable setup. Here, an n tuple of commuting contraction V acting on some Hilbert space K is called a dilation of n tuple of commuting contraction T if, as previous, T power K is the compression of V power K. But here K is the multi-index and T power K and V power K is defined in this way. When V is an n tuple of isometries here, then V is an isometric dilation of T, and if V is an n tuple of unitaries, then V is a unitary dilation of T. Here also extensions and co-extensions are dilation, and extension means it is extension component wise, and co-extension means V star is an extension of T star. Now question is, when an n tuple of commuting contraction has an isometric dilation. In 1953, Nash shows that a contraction on a Hilbert space always has an isometric dilation. That means if we consider a single contraction on a Hilbert space H, it has an isometric dilation. And due to n-do, every pair of commuting contractions T1, T2 has an isometric dilation. But we cannot generalize these results for multivariable because there are counterexample of parrot which shows that for n greater equals to 3, an n tuple of commuting contractions does not possess an isometric dilation in general. Now look at the corresponding von Neumann inequality. So recall what is von Neumann inequality. An n tuple of commuting contraction T satisfies von Neumann inequality if operator norm of Pt is dominated by the subnorm of the polynomial P over the unit polydisc. And this happens for all polynomial in n variables. In 1951, von Neumann proved this inequality for single contraction. Later, it immediately follows from the isometric dilations of Nash. And due to the isometric dilation result of n-do, as every pair of commuting contraction every pair of commuting contraction has an isometric dilation, then the pair satisfies von Neumann inequality also. And due to Harpulus, von Neumann inequality does not hold in general for n greater equals to 3. And it has been seen that, and I have already mentioned that von Neumann inequality is an immediate consequence of having isometric dilation. That means if a tuple of commuting contraction has an isometric dilation, it satisfies the von Neumann inequality. So we have three things. Isometric dilation does not hold for n greater equals to 3 in general. Von Neumann inequality does not hold for n greater equals to 3 in general. And von Neumann inequality is an immediate consequence of having isometric dilation. So this leads us to investigate isometric dilation and von Neumann inequality for a tuple of commuting contractions, for a class of tuples of commuting contractions under certain positivity assumption. And the positivity assumption we consider is known as Szego positivity. So, before going into Szego positivity and before going into our class, we need to recall the definitions of Hardy space and the multiplication operator, etc. So that the Hardy space and the multiplication operator and some results already have been introduced by some previous speakers. So I'm just recalling here. For unit disks, Hardy space over unit disks denoted by H2D is the set of all analytic functions on unit disks such that coefficients are square summable. And whenever we are talking about analytic function, it has a power series representation. So this is nothing but the set of all convergent power series on unit disks such that coefficients are square summable. Now generalizing this notion for a Hilbert space E, the E-valued Hardy space over the unit polydisc, which is denoted by H2EDN as the set of all convergent power series in n variables, where the coefficients coming from the Hilbert space E such that the coefficients are square summable. And it is an well-known fact is that Hardy spaces are reproducing kernel Hilbert spaces. So it has a kernel function. And the kernel function of this Hardy space H2EDN is Sn times identity of E, where Sn is the Szego kernel on the unit polydisc defined in this way. Sn ZW is product of I minus Zi Wi bar inverse. And taking inverse of this kernel, we have a polynomial product of I minus Zi Wi bar, and in that polynomial replacing Zi by Ti and Wi bar by Ti star, we have this expression for a tuple T1, T2, Tn. And this expression is a finite sum, and the sum varies over all subset F of the set 1 to n. And where TF is defined in this way, for a subset F of 1 to n, TF is the composition of these operators T of A1, T of N1 up to T of Nk. And this expression turns into an operator, and whenever this operator is positive, we say T satisfies Szego positivity. And we denote this expression as Sn inverse Tt star. Now let us look at how this expression look like in simpler cases. For n equals to 2, that means we are considering a pair of commuting contractions T1 and T2. For T1 and T2, S2 inverse Tt star is nothing but this expression. So for empty set phi, we have identity. For singleton 1, we have T1 T1 star, and for singleton 2, we have T2 T2 star, and the full set 1 and 2, we have this quantity T1 T2 T1 star T2 star. And whenever this expression is positive for this pair, we say this pair satisfies Szego positivity. Now multiplication, multipliers and the multiplication operator defined in the similar way as one dimension. Here is the definition of multiplier. A function is called a multiplier if phi of f belongs to the a function phi on the unit polydisc is called a multiplier from the Hardy space H2 E1 dn into H2 E2 dn if phi of f lies in the Hardy space H2 E2 dn. And with respect to a multiplier, one can define multiplication operator in the similar way, and one can talk about their norm equality. That means subnorm of the multiplier is equals to the operator norm of the multiplication operator m phi. And here also a multiplier phi is called the inner function if the radial limit of the multiplier is isometry almost everywhere in the distinguished boundary of dn, which is Tn. That is the unit torus, n-dimensional torus. And useful fact is that phi is an inner function if and only if m phi is an isometry. And special type of multiplication operators are called shifts, and here we define shifts coordinate wise that are the multiplication operator with respect to the coordinate functions. And n tuple of Hardy shifts mz1, mz2, mzn on the Hardy space H2 dn is a commuting tuple of isometries, and one can check that it satisfies Szego positivity. Another fact is that multiplication operator, Hardy shifts always commutes with the multiplication operator with respect to some multiplier, and the converse is also true. If an operator commutes with the Hardy shifts, that turns into a multiplication operator with respect to some multiplier. Now we define pure tuple. An n tuple of commuting contraction T1, T2, Tn is pure if it is pure component wise. That means for all I and for each h belongs to the Hilbert space H, Ti star m h norm of this thing tends to 0 at m tends to infinity. So what are the examples of pure operator? Let's take a contraction T and let's take R lies in between 0 to 1. Then RT is always a pure operator. And also one can check shifts on the Hardy space is pure, and hence the tuple mz1, mz2, mzn, n tuple of Hardy shifts on the n-dimensional Hardy space is a pure tuple. Here is an useful and interesting dilation result of Couto and Vasilescu. According to them, if an n tuple of commuting contraction T1, T2, Tn be a pure tuple and satisfies Szego positivity, then this tuple can be dilated to n tuple of Hardy shifts on some Hardy space over unit polydisc, where the coefficient space of the Hardy space is script dt, which is the defect operator with respect to the tuple T, and which is defined by range closure of the Szego expression Sn inverse Tt star. And moreover, this dilation is a coextension, and since n tuple of Hardy shifts is a tuple of commuting isometries, this is an isometric dilation result. And also this theorem tells us that n tuple of Hardy shifts on some Hardy space form a model in the class of Couto and Vasilescu. That means if we restrict, if we compress the n tuple of shifts on some coherent subspace of some Hardy space, they have this property: they are pure and they satisfy Szego positivity. Now, generalizing the class of Coutu and Vasilescu, we define a class, namely, we define our class, namely tau n pqh, and find explicit isometric dilation and von Neumann inequality for our class. So before going into our class, we need to introduce some notation. So for an n-tuple of commuting contraction T1, T2, Tn, and for each I, we denote Ti hat as the n-1 tuple coming from the tuple T, where Ti is missing. And with this notation, we define our class tau n pqh. So for different P and Q lies in between 1 and n, we define tau n pqh as the set of all n-tuple of commuting contractions such that Tp hat and Tq hat satisfy Szego positivity and Tq hat is pure. That means two different n-1 subtuples satisfy Szego positivity and one of them is pure. So obviously this is a generalized class of Coutu and Vasilescu. And also this class densely contains the class of Vinnikov and their collaborator, and their class is denoted by P and PQH, which is the set of all n-tuple of strict contractions such that Tp hat and Tq hat satisfy Szego positivity. So observe that the Szego positivity conditions are same for both of the classes. The difference is that they consider strict contractions. Instead of that, we consider one of the subtuple is pure. So since strict contractions are already pure, their class contained in our class tau n pqh, and also the containment is dense and also the containment is proper. And one example is that if we consider n-tuple of adhesives on some Hardy space, then the tuple belongs to our class but not in the class of Vinnikov and collaborator. And in this generalized class, not only we find the isometric dilation, we find them explicitly, and which has some bigger impact in the corresponding von Neumann inequality. Now it is sufficient to work with the class tau n 1 and h instead of tau n pqh so in particular, observe that tau n 1 and h is the set of all n-tuple of commuting contractions such that first n-1 tuple Tn hat and last n-1 tuple T1 hat satisfy Szego positivity and Tn hat is pure. Okay. So why this is sufficient to work with the class tau n 1 and h instead of this class? Because if we let's take a tuple in the class tau n pqh, then interchanging Tp with T1 and Tq with Tn, we can always look at the tuple in the class tau n 1 and h. So our next result will be in terms of this class tau n 1 and h. So first we will find isometric dilations for the finite rank tuples in the class tau n 1 and h. So what are the finite rank tuples in the class? T belongs to our class is called finite rank if defect space with respect to T1 hat and defect space with respect to Tn hat are finite dimension. And for finite rank tuples, we have this isometric dilation result. Let's say T be a finite rank tuple in our class, then T dilates to n tuple of commuting isometries on some Hardy space where the tuple consists of Hardy shifts and some multiplication operator. Observe that the tuple T1 to Tn lies in the class tau n 1 and h. That means first n-1 tuple satisfies Szego positivity and pure, right? So using the Coutu-Vasilescu result, we can dilate them n-1 tuple of Hardy shifts. So now we left with the last component Tn. So we have to dilate to some operator and that has to commute with the other shifts. So we have observed that that operator which commutes with the shifts is the multiplication operator with respect to some multiplier. And since we are also expecting the dilation is a isometric dilation, MP has to isometry. So phi has to be inner function. And our theorem says that phi not only an inner function, it is an inner function with respect to the single variable Z1. And since all the operators are isometry, this is an isometric dilation. And the explicitness of this dilation helps us to refine the von Neumann inequality for the finite rank tuples in terms of an algebraic variety. That means what? That means let's say TBA finite tuples in our class. Then there exists a variety V such that von Neumann equality for the tuple holds on the variety V instead of the polydisc D itself, and the variety lies inside the closure of the unit polydisc. And moreover, if Tn is a pure contraction, so according to the assumption of our class, first n-1 tuple was pure, but if we impose the purity condition on the last tuple, then the variety V has the form this, where V prime is a distinguished variety in the unit pi disk, and V has the form V prime times n-2 polydisc. So what is distinguished variety? A distinguished variety is an algebraic variety V with respect to some polynomial P such that V closure exceeds the boundary of D2 through distinguished boundary. That means V closure intersection boundary of D2 is same as the V closure intersection distinguished boundary of D2. Now using a different method we find, so that was all about finite tuples of our class. So now we need to find isometric dilation for the general tuples in our class. So using a different method we find isometric dilation for general tuples in our class tau n 1 and h, and we find them explicitly. So let's say TBA finite tuples in our class, then T dilates to n tuple of isometries on some Hardy space, on some e-valued Hardy space over n-1 polydisc, where the isometric tuple consists of Hardy shifts and multiplication operator with respect to some phi1 and phi2, where phi1 and phi2 are inner polynomials in Z1 variable of degree at most 1, and not only that, they satisfy some interesting property. If we multiply them, they commute with each other, and the multiplication turns into the multiplication with respect to the variable Z1. And this isometric dilation result tells us that the tuple m phi1 and the shift and the tuple m phi, where phi1 and phi2 are inner polynomial in Z1 of degree at most 1, and the property satisfied by them. So this tuple forms an model n tuple of isometries in our class tau n 1 and h. And also, as an immediate consequence of the isometric dilation result, we can say the tuples in our class satisfies the von Neumann inequality. So here are some references. The content of my talk can be found here, and the result of Couto and Vasilescu can be found in this paper. This finishes my talk. Thank you. Thank you for your attention.
Thank you very much. Questions, comments, suggestions? So there is a question in the chat. What is the von Neumann inequality useful for?
Von Neumann inequality useful. Sorry. Can you repeat the question?
What is the von Neumann inequality useful for? So
it von Neumann inequality basically tells us that what are the spectral set for the operator, right? Every contraction satisfies von Neumann inequality means the unit polydisc is a spectral set for the contraction. Similarly, if a tuple of commuting contraction satisfies von Neumann inequality means the unit polydisc is a spectral set for the tuple of commuting operators. So somehow it reveals the structure of the operator or the operator tuple.
Thank you. More questions, comments? Well, if not, let us thank. Okay. So yeah, so there is a comment by Javad that it's useful for introducing a functional calculus, at least, of course. Thank you, Javad. And so more comments.
Sorry for function at least. Sorry, I didn't get the comment. So
so the comment was that it's useful for introducing a functional calculus. Just that. Yes.
Okay.
Well, if there are no more questions, let's thank Sibaprasad again.
Thank you.
And